Yeah, so my name is Lina Roald, and I've been leading this effort for this PSCC survey paper on power system optimization under uncertainty that we are going to present to you today. So the title of our paper is Power System Optimization Under Uncertainty, a Review of Methods and Applications. So my name is Lina Roald. We have David Pozo here on the screen. We have Anthony Papavasiliou, Dan Molzahn, Jalal, Kazempour, and then also Antonio Conejo has been working with us on this paper. Unfortunately, he was not able to make it today. All right. So to start this presentation, I know we're starting a little late, so what we are going to do is that we're going to try and keep it relatively short so we have some time for discussion in the end. And so I'm going to start here just with a little bit of a motivating example. Because when we are talking about optimization under uncertainty, and power system optimization under uncertainty in particular, kind of the key thing that we are facing is that it is hard to make decisions when you do not know the future. And in many situations, you have to make a decision now, and the decision that you make now is going to impact what happens to you in the future. And so to give an example here that might have been something many of you have thought about, I think also many people who are maybe not here but intended to be here have thought about, is the question of when, with COVID and travel restrictions, should I plan to travel to PSCC? So if you looked at this and thought about your registration, you know that there are different fees for registering for the conference early or late. And so the thing that happens is that if you say to yourself, if I register now, registration is going to be cheaper, but if I'm not able to travel, I might lose that money. Alternatively, I can wait with registering, but then I'm going to lose the difference, right? I will have to pay more. And so the question that maybe some of you have asked yourself is, what is the optimal decision in this case? You can think about that for a second. I don't know what you all chose to do. I haven't talked to the organizers about the number of people who chose to register early and late. But we will just look at this example for a second. So of course, when we are looking at this, whether or not you choose to register early or late depends on the consequences of making the wrong decision. So essentially, how much money am I going to lose? And of course, also, probably you would be thinking about what is the probability that I'm going to go to the conference. So we can think about this in different ways. So if I am a student and I can choose to minimize the expected loss of money that I might expect from registering, I would have to consider the probability of going. Say, I know it's about 80% sure that I'm going to go to the conference. And so I can calculate the expected loss if I choose to register early. In this case, this is going to be the fact that I might register for 350 euros, but there's a 20% chance I'm not going to use it. So there's a 20% chance I'm going to lose this money. Or if I go, of course, then I don't. There's an 80% chance that that was a good investment to spend those 350. And so essentially, the expected loss here would be 70 euros. If I register late, of course, if I don't end up going, then I don't lose any money. But if I do end up going, then I would lose the difference between the early and the late registration fee, which for a student fee is 450 euros, and there's an 80% chance, because I plan to go, that might happen. And so in this case, the expected loss is 360 euros. Now, I can keep doing this, and I can look at what if I have a different probability. Well, then these numbers end up being different because the probabilities here would be different. And I can also calculate it for a regular registration, and in that case, you can tell that the numbers end up being quite different because the early fee is already pretty high. And now I see that on this slide it says here that the late student fee is 350. So maybe I did this completely wrong. I don't know how I missed that. Sorry. Okay, anyways, if it was 800 and you have to do the regular fee, then the students, you should always, the thing that happens here is that as a student, you should always register early, and regular attendees should always register late. Okay, so, or not always. It depends, of course, on the probability. Now, if I want, I can think about different things. So here I said I will minimize my expected loss. I can also try and minimize my worst case loss. And in that case, what I think about is that I have two options that can happen. So I have an uncertainty set. There are two possible realizations that can happen here. I can choose to go or not go. And in that uncertainty set, so I have to choose look at what is my worst case, or what is my loss if I register worst case loss in both of those cases. And then I again can do this calculation. And again, I find out that if I register early, or if I'm a student, I should register early. If I'm a regular attendee, I should register late. And so this is kind of so the difference here between trying to minimize the worst case loss is that I didn't take into account the probability. And that can be a helpful thing to do if I maybe haven't really quite made up my mind, if I'm not really good at thinking about the probability that I will end up going to the conference, because maybe I really want to go to the conference, but I cannot decide what the COVID virus is going to do, nor what my government is going to decide in terms of restrictions. Okay, so this was just a motivating example to wake you up a little bit here in the morning. So now I'm going to get to the actual scope of this paper. So in this paper, we've been trying to do three things. So the first part of the paper is that we are trying to, in the first part of the paper, we are trying to review common modeling, reformulation, and solution techniques for optimization under uncertainty. So this is a pretty broad overview. In the second part of the paper, we are reviewing some examples of existing applications, including some references. And then we have a third part where we're discussing ongoing and emerging directions for future research. And I will just say that by definition, this is not a paper that covers everything, because this is too big of a field, of course, to try and capture in one paper. But what we've been trying to do here, and in particular in this first part of the paper, we've been trying to focus on providing a basic understanding of a relatively wide range of different modeling and solution techniques for optimization under uncertainty, and then provide references for further reading. And I just want to say this is not a tutorial. It is not meant that you read the paper and then you know everything how to do things. It is really meant to kind of more provide a panoramic view across many different kinds of reformulation and solution techniques. And the target group that we had in mind when writing this is really our own students. So people that we think are familiar with electric power systems and know something about optimization. So someone who is interested in getting into this field and learn about power systems optimization under uncertainty. And so we hope that this is going to be helpful not only for us, but also for many of you. So this is a plug to sort of maybe take a closer look at that paper. And so I will talk a little bit more about the type of methods that we're covering. Then in the second part here, what we are going to do is that I will have each of my co-authors, including also David, give a short presentation of one application. So this is not everything that is there in the paper, but some selected ones. And then in the end, we want to open the discussion also with you to talk about where this is going and sort of some future directions. Okay, so just to start a little bit about and give you a brief overview of this sort of common modeling, reformulation, and solution techniques. So when you start out thinking about a power systems optimization problem under uncertainty, the first thing you try and do is, of course, think about, okay, what is the problem I want to solve? And one of the key questions for a problem that has uncertainty in it is, what is the source of uncertainty? And so in power systems, there's obviously many different kinds of sources of uncertainty. So we can have contingency scenarios where we have outages. We can have renewable variability and uncertainty forecast errors from renewable energy generation. We can have uncertainty about the load in the system, or maybe the behavior of demand response resources. Maybe if you are thinking about trading, we don't know the future electricity prices. And of course, there's also some longer term trends, for example, such as climate change trends and extreme weather, or also technology development and so on, that can play into this problem. So there's a wide range of different sources of uncertainty that we can treat in a power system optimization problem. So typically, we don't look at all of them at once, right? We look at one or two, maybe. So once we know what kind of uncertainty we're looking at, and the next question when we're trying to model an optimization problem under uncertainty is the question of how are we going to represent this uncertainty in our problem, or what is a natural way to actually present it. And so depending on the source of uncertainty, so for example, if I'm looking at renewable energy generation, this is a relatively continuous source of uncertainty that is well captured by something like a probability distribution. So I might choose to look at a continuous probability distribution for renewable energy generation. I can characterize that, for example, using moments, or so the mean and standard deviation, and also covariance of the if there's a higher dimensional uncertainty distribution. Or in some cases, I will not know what is actually the true probability distribution. So I might instead want to consider a family of distributions. Maybe I don't know exactly what is the distribution, but maybe I know approximately. Maybe I know that the mean is in a certain range and the standard deviation is in a certain range. Alternatively, I can also try and represent uncertainty using scenarios. If I have discrete uncertainty, like for example contingencies, we're used to think about those as discrete scenarios that can happen, possibly with a given probability. But I could also, even if I had a probability distribution, I could also use scenarios, either sampled or sort of a discretized distribution, in order to try and represent that. And then finally, also, if I'm interested, if I don't have very much probabilistic information at all, or I am looking at a problem where I really care about not having constraint violations or very high cost, and maybe I instead want to look at something like a robust uncertainty set, where I say, okay, here's the whole range of realizations of uncertainty that I want to hedge myself against. And so these are just some 3 different ways of thinking about representing uncertainty in an optimization problem. So then when we come to actually formulating the optimization problem, I will just show you here, again, also sort of a stylized problem over here. So this is a problem where you see we are trying to minimize the cost here subject to a set of constraints. And so I'm going to go through this problem in a little bit more detail. So in this problem, we have a certain set of parameters and decision variables. So we have a set of uncertain parameters xi. So we have entered, those are listed here inside the cost function and also in the constraints. Those are not decision variables. We cannot choose what xi is. Nevertheless, we list it here as an argument in those functions just to make it explicit that those are functions that depend on the realization of xi. Then we have first stage decisions. So these are or so-called here and now decisions. So these are the decisions that we have to take now. I cannot wait. I have to decide now whether or not, for example, I'm going to build a transmission line that I'm going to use for the next 20 years. I make the decision to build it or not now. And these variables are called x here in blue. And then we have our second stage variables, which are the decisions which we can wait and see, or so-called wait and see decisions, which are decisions where we can see, okay, how did our uncertainty realize? And are we now able to actually, how are we able to react to those uncertainties in the best way? So these are denoted by y xi here. The subscript xi just indicates that these are decisions that can depend on the realization of xi. Okay, and then one thing to note here is that the first stage cost and constraints here, they are deterministic because we know them. When we make the first stage decision, for example, if we make an investment, I know the cost of that investment, and I maybe have also some constraints on how much large investments I can make and how much money I can spend. And so these are typically known at the time when we are making the decision. And then we have the second part here, which is the second stage cost and constraints. And those are the ones that we are only going to know with certainty once the uncertain parameter xi has been realized. And so these are the ones which we can't just really state the cost here or state the constraints, because since we don't know what xi is, that would be an ill-defined problem. And so that's why we have these risk operators here, where our cost here represents a risk operator, something that helps us measure the risk of having a particularly high cost due to unfavorable realizations of xi. Or we have this risk operator R violation here, which has to do with the risk of constraint violations. And so a very important question, once we have thought about what are the sources of uncertainty that we will integrate, what are the constraints and the objectives that we have on our problem, is also the question of how do we actually measure this risk. And so there's a number of different ways in which we can do this, and this is where we are in this paper trying to take a rather panoramic view and also talk about many different, because there's many resources and papers that will talk about one in individual ways, but here we try to kind of gather some of the most common ones together. And so we can roughly, if I think about this, I can think about it roughly as two categories here. Here is a sort of kind of formulations that try to address the risk of having very high cost, or the risk of constraint violations. And on the risk of high cost, if I can consider risk-neutral problems, where I'm essentially looking at minimizing, of course, the first stage cost, but the second stage cost in terms of what is the expected second stage cost. And in this case, I'm actually considering all the realizations of the uncertain variables here, and I'm weighing both the positive and negative outcomes that I can get. So even if I had a very favorable realization of Xi, I'm going to account for that in this case where I'm looking at the expected cost. But I'm also going to count the situations where I have very unfavorable realizations of Xi. A risk-averse formulation, often where the risk is often measured in, for example, with variance in cost or the value at risk or so-called conditional value at risk. These are formulations where we are more focused on limiting the chances of or the size of the cost in the worst cases. So we want to kind of limit the probability or the size of this tail here of the distribution towards having very high cost. And so one common risk measure for that would be the CVAR or conditional value at risk. Then we have distributionally robust optimization, where we don't know exactly here. So here I've been assuming that I know the probability distribution. In distributionally robust optimization, I don't really necessarily know exactly what the distribution is. And so I think about an ambiguity set where I have multiple different distribution, and I can, for example, look at the worst case expected cost across all those possible distributions. Or I can go to robust optimization, where I'm not even going to try and assess necessarily what those probability distributions are. I'm just going to create an uncertainty set, and I'm going to say these are the range of realizations that I want to hedge myself against. So that is on the risk of high costs. On the risk of constraint violations, common formulations to try and ensure that we don't have too frequent or too large violations have to do with, can be, for example, chance constraints, where we are looking at the probability of constraint satisfaction. So we will, for example, look at what is the probability that we exceed the limit. I can then also have the distributionally robust version of this, where I look at what is the worst case probability across many different distributions. And then again, I can also have an uncertainty set and then just make sure that I don't have any constraint violations for any realization inside that uncertainty set. And so this was just sort of, again, a little of a panoramic. So in the paper, there is, of course, more details about this. There exists also other formulations, and in the paper, you can also find more discussions on common reformulations and solution algorithms for these different types of problems. So that takes us to the second part of the paper. So what we will do now is that we will review some examples of existing applications. I will say here that many of you maybe work on optimization under uncertainty, and there's, as we saw, a large range of possible uncertainty sources, a large range of possible problems, as there is a large range of problems in power systems overall. But so what we are doing here is that we will focus on power systems operation and planning from sort of the perspective of a system operator. And so that is the perspective of this presentation. It's also the primary perspective in the paper, but we have some other examples there as well. So here is a brief overview of applications in this presentation. I don't expect you to actually try and read all of this, but this is just an example of the different way we characterize these different problems in our paper. And so what we're going to do is that we're going to have Dan first present about security constraint, optimal power flow. Anthony will then present about multi-area reserve dimensioning. Jalal will talk about distributionally robust optimal power flow, and David will talk about long-term planning. And so the reason we chose these different formulations here is that they cover some different sources of uncertainty. So we have contingencies, we have total power imbalance, we have renewable energy focused ones, and then in the long-term planning, we have both long-term and short-term uncertainty. And so we wanted to cover different types of uncertainty here, and then also kind of try and build this up in a way where we start with some kind of more maybe known and familiar applications towards the more exotic. Okay, so with that, I will hand it over to Dan.
Great. Well, thanks, Lena. So one application that we don't often, or don't, at least I don't often think about as a problem under uncertainty, an optimization under uncertainty, but truly is the security constrained optimal power flow problem. So oftentimes, you know, at least the way that I would teach this in my classes, and I think it was taught to me, is, well, this is just a criterion. You have to satisfy security constraints, and that's the rules. But really, there's value in thinking about this as an optimization problem under uncertainty, where really what we have in this case is a robust problem to a discrete uncertainty set. And so the kind of traditional way that we might formulate this problem is we're going to minimize cost of generation, maybe in our base case. Then we have a set of contingencies. And each of these contingencies you can think of as potential uncertainty realizations. And we're going to be robust against any of these uncertainty realizations occurring. And then, you know, we have to couple the base case variables to the contingency problems, the variables and constraints in the contingencies. And effectively, the way we do that is via something that looks a lot like a recourse policy. You know, we talk about this as preventative security versus corrective security, and trying to determine what that coupling looks like. But really, it's a recourse policy. And so this has taken on a lot of interest, at least especially in the US, I should say, with this RPE Go competition, the grid optimization competition. There's been several challenges in this competition. I don't know if this has been followed here in Europe as much, but this has gotten a lot of attention on the other side of the Atlantic. And we had challenge 1, which was a preventative formulation, challenge 2, that was a corrective formulation. And this really ties back to what Lena was describing as, you know, how do we handle these wait and see decisions? Are we allowed to optimize over these, or are they essentially policies that are fixed from ahead of time? And so the way that we solve these problems is also, you know, you can think about this very analogously to a robust optimization problem, or stochastic optimization problem. So I put up an example algorithm here where what we would do is perhaps we solve the base case, ignoring the contingency scenarios. We come up with some initial contingency ranking to try to prioritize which contingencies we're going to consider first. We then select among that ranking to try to determine which of the contingencies we want to see which ones have violations. We then might add those violated contingencies back to the base case and solve a larger problem, and then iterate between selecting new contingencies and evaluating the impacts of the contingencies we haven't considered yet. A nice feature of this is we can do a lot of this work in parallel. And that turned out to be quite important in the competition to do that efficiently. But in the context of a stochastic optimization problem, you can think of this as, you know, many of these steps are adaptive sampling steps. We're trying to identify which of the uncertainty realizations that we need to consider, or which to consider first. And then other steps in these algorithms are analogous to uncertainty propagation. We're seeing what are the impacts of our contingency scenarios, our uncertainty realizations, on our base case operation. And so this analogy from a security-constrained optimal power flow to stochastic optimization, it can motivate alternative formulations to this problem. And so, for instance, rather than trying to have a robust formulation, one might want to try to balance the contingency likelihood with the impact, or the likelihood and impact of the contingencies, using some sort of risk function. So there's been all sorts of work that has been proposed on this by sort of interpreting the security-constrained optimal power flow problem as more of a stochastic problem, where what you might want to do is balance the likelihood of the contingency occurring. So you're not necessarily robust to every contingency, but you consider the probability and risk. We put a selection of papers up here. There's a whole series of work on this. Of course, the challenges in doing this are that, you know, you're increasing the complexity of the problem. There's challenges in data availability. You need to sort of estimate these failure probabilities and the impact in terms of load shedding. But, you know, this is a trend of work that if you interpret this problem as a stochastic optimization framework, then there's lots of tools that you could apply to it potentially. So that's it for me today. Next we'll hear from Anthony on multi-area reserve scheduling.
Great. So I'm going to talk about an application which maybe is more interesting to the EU context, but maybe, hopefully I'm wrong. The reason I'm saying it's maybe more interesting to the EU context is that due to recent legislation, well, not so recent, but quite widespread legislation, in particular the System Operating Guideline, Article 157, and more generally, due to renewables integration, TSOs are encouraged to coordinate more broadly in Europe. So part of that is both sharing reserve and sharing balancing energy. When you're thinking of sharing reserve, there's two words that are used. One is sharing and the other is exchange. You can think of one as let's use the same reserve capacity, but hopefully not in the same moment. That's sharing. Exchange is let me as a TSO use reserve from a neighboring member state, but with exclusive access. I'm going to focus on sharing. And what Article 157 says is that you should, when you're doing this exercise of sharing between countries, or even within your zone, you should size so as to meet imbalances 99% of the time. That's enshrined in very broad EU law. That's basically a chance constraint. The reason the problem is complex is that the impact of the network can have quite significant implications. If you think of a single area and how you size it, you think of this example here where you have normally distributed imbalances, then just taking two areas and assuming they operate independently means you apply basically a quantile. You look for the quantile of the distribution of imbalances for each area, and you get a total of 658 megawatts for meeting the reliability criterion of the previous slide for both areas. Then if you merge these areas, assuming that the capacity is infinite in the line that's connecting them, imbalances cancel out within the different areas, and basically they're doing some of the work that the reserve is supposed to be doing. So you can get away, again, by applying this quantile criterion, with a 437 megawatt total reserve, which is a significant savings, again, because the imbalances are doing part of the work of the reserve. Now, if you introduce a line between the two areas that has, for instance, a capacity of 80 megawatts, you have to start worrying about combinations. Is the line going to carry balancing energy or not? In which direction? And is it going to be is the capacity going to be violated or not? So this graph shows you how you would want to approach the solution graphically. You can only do this analytically for very simple instances. And that's where you might want to approach the problem instead as a chance constraint formulation as a mixed integer linear programming chance constraint formulation. So you introduce binary variables to indicate whether you're failing an imbalance or not. And you're aiming to minimize the total reserve capacity that you're carrying in an LFC block, for instance, making sure you meet imbalance, power balance at each zone. You only activate balancing energy to the extent of the reserve that you've committed, and you allow yourself these failures that if you activate them with setting the binaries to 1, it allows your slack variables to become non-zero and to meet the power balance constraint. And then this is a chance constraint here that says that you can only fail so many times, and as long as you respect that constraint, you're not violating the SOGL criterion of 99.x%. This is a difficult problem, and you can tackle it with a heuristic, like using a linear relaxation. That's what we did in collaboration with the Swedish TSO, where we showed that effectively by sharing reserves, you can quite narrow down the reserve requirement in the Swedish area, actually 77%, as opposed to if you take SE1 through SE4, the 4 Swedish zones, and size them independently. And what's really promising and interesting, and I think is an inspiring research direction, is other mixed integer programming techniques. For instance, you can implicitly characterize this set of feasible reserve sets, which gives rise to mixing sets for which we have convex Hull characterizations. But if then you introduce a cardinality constraint on top of that, you get facet defining inequalities, and you can lift that to an extended space and come up with a very efficient exact solution. So that's some work that is ongoing, and we're in discussion with the entire Nordic area about implementing this concept to the entire Nordics. But of course, there's the complexity that the Nordic network is actually meshed and no longer radial, which raises interesting challenges in relation to the approach that I just described. I'm going to stop here and hand it over to Jalal for the next part.
Okay, thank you, everyone. My job is to make sure that, to promote distributionally robust optimization in the next 5 minutes and to make sure that you will like it. If you already know what DRO, distribution robust optimization is, you can relax the next 5 minutes. As Lena said, there are many times that you have uncertainty and you don't know what the probability distribution of your uncertainty is, especially if you have the lack of data, historical data. The first day on Monday, we talked about extreme events, low probability, high impact events or rare events. In those kind of cases, we may have not enough data, so we don't know exactly what kind of distribution we can consider for our sources of uncertainty. And OPF problem, maybe also you can think the same. I mean, it's not necessarily that we know our probability distribution for renewable supply is or other potential source of uncertainty, right? So in that cases, maybe we could say, okay, well, I don't know exactly what probability distribution I have, but maybe I can guess, maybe I can say, I can find a family of distributions that may represent my sources of uncertainty, right? And then based on this discussion, this type of thinking, people in OR community, they invented distributionally robust optimization, right? So in distributionally robust optimization, instead of having one single probability distribution, you may have multiple or even infinite number of probability distributions. So the beauty of distribution robust optimization is that endogenously, you are trying to find the worst distribution that you have in your family of distributions, that we call it ambiguity set. And then when you find the worst distribution for yourself, then you try to optimize your optimization in expectation against the worst case distribution. And the good thing is that it's a very general model. If you start shrinking the number of your distributions and just to leave one, then simply your optimization problem becomes stochastic programming, right? That you are trying to find, to optimize an expectation, and your constraints are gonna be a chance constraint that Anthony talked about. And if you start increasing the family of your distribution, you are going towards robust optimization that after me, David will talk about. So, but the big challenge of distribution robust optimization is also, you can think of, for example, in the OPF problem, how we can build the ambiguity set, how we can end up in a family, a set of probability distributions. So in OR community, and also there are many of you expert in that, there are two common ways. One is that saying, okay, well, I don't know what exactly my renewable supply uncertainty is, but I know what the mean and covariance is based on the empirical data. And then you can say that, okay, I generate infinite number of distributions that follow the same mean and covariance, right? Or you can do better. Maybe you can say that, okay, I know the empirical distribution, not necessarily defining by Gaussian or whatever, just I have some samples. And then I can use some elegant methods. I can use some distributional distances like Wasserstein metric or whatever, and then say that, okay, any kind of distribution that they are close enough to my empirical distribution, they are in my ambiguity set, right? So it's really nice to be creative and see, okay, what I like to put in my ambiguity set, but you have to make sure that when you have distribution robust, you will have minimax objective function, you will have distribution robust chance constraint. So you have to make sure that you will be able later to reformulate it in a convex way, right? So we have to be very careful how we are defining our ambiguity sets, right? So this is my last slides, but okay, you can consider it for distribution robust OPF or any kind of problems in power systems with that we don't know exactly how we can describe our uncertainty, right? So we are minimizing our first stage constraint, and then we are trying to minimize the worst case cost. I mean, we are trying to find the worst case distribution, and for that we are trying to maximize an expectation. And then we have first stage constraint, and the second stage constraint, they are in the form of distribution robust chance constraint, just to make sure that they are not infinite dimensional, right? So again, like for objective function, you are trying to find the worst distribution in the family, and then try to make sure that, those constraints are valid in form of chance constraint for the worst case distribution. So the last things, the common way to solve this kind of optimization is to use a affine policy trick. We like it not because we can make it convex, but also it's very practical in power systems. For example, you can use it in OPF problem for reserve allocation. I mean, you can say that, for this generator, my affine policy after solving the problem is 0.1. What does it mean? It means that any kind of imbalance that we will have in the power system, the 10% of the imbalance will be compensated by that specific generator, right? And then we don't need to re-optimize the problem in the real-time stage, because in the scheduling stage, we have a policy for every generator, how they have to compensate imbalances. And then the very common trick in OR community to deal with this distribution robust optimization is to use CVAR approximation. I mean, in the paper, there are more details, but this is what I could do in this 5 minutes. Thank you so much for your attention.
So yeah, we have one more, and I would just ask, are you able to get David back?
Can you hear me?
Yes, we can hear you. Okay, so let me know when to click.
Yeah,
David.
Nest. Yeah, so I'm going to talk about long-term planning and how this uncertainty or this framework that we are presenting here can be considered in the long-term planning. So long-term planning can be transmission expansion planning problem, generation expansion planning problem. Those type of problems basically have 2 components, capital cost and operational cost. This problem is very natural fit into a stochastic framework. And the first stage costs are very close related with investment costs, while the second stage is related with the operational cost. So it is common to use like typical days, typical hours to represent these operational costs, but there are other ways, a more sophisticated way and frameworks of stochastic optimization to represent the operational cost. So next. So long-term planning basically is a centralized problem. It is a complex engineering system which is interacting with other complex systems. So in somehow, we may expect to have a large number of parameters that can become uncertain or stochastic. Like we have standard parameters like renewable generation, what will be the location of new facilities, what will be the demand, or even the price of some technologies, price of the fuel, price of the gas, we will have available gas or not, so on and so forth. So in that way, we can distinguish 2 types of uncertainty. So like what is called long-term uncertainty, which typically realize once, like for example, what will be the price of lithium-ion batteries? So we will observe in time for the next 20 years, one realization. But also we can use, we can have short-term uncertainty, like we will observe many times, we will have many realization of this type of uncertainty parameter. For example, wind generation in a specific location. So along the year, we will have different patterns, different values of this wind farm. So industry and academia have been using different type of criteria for dealing with this long-term planning problem. So in general, what is called a scenario planning in the industry is the way that they have been dealing with this uncertainty. And a scenario planning basically is a narrative of the future. So we will see the future like a business as usual. So having some projections, we will have some disruptive technology that will change everything. So this is kind of the way of industries looking at the long-term planning decisions and looking at these scenarios. Well, in academia, we used to have more about the stochastic framework that we have already seen. Next, please. So investment can actually be greatly impacted with events that have a high impact but low probability. And this is more especially important in the cases like we have consideration of robustness, or we want to have some level of resilience. So we can end up with a large amount of transmission lines that we have to build, a lot of generation that we have to build also to have a resilience system or planning system. So how to deal with that? And also I'm showing here in the right-hand side a plot of what is the projection of the total wind capacity generation globally, projected by the World Energy Outlook year by year. And then you can see like every year they were underestimating. And the World Energy Outlook is probably one of the most trustful reports that we can have right now. So it still is challenging to quantify uncertainty even from experts. Experts are usually part of this formula in the long-term planning, especially in the implementation in the industry. Next, please. So what is the actual cutting-edge research? So what we can find now in the community? So we can observe there are many long-term planning frameworks for dealing with uncertainty, like distributionally robust optimization, adaptive robust optimization, stochastic optimization, chance constraint. There are also a combination of those frameworks, like why we can actually combine robust optimization with the stochastic optimization for several reasons. The way that we capture this long-term and short-term uncertainty also is kind of cutting-edge research that we see now in the academia. And there is also a trend, but this is general trend in power system, that to build larger models, just to include more details or different type of interaction with other systems, or like, for example, with distribution system, multi-energy system, or modeling other technologies. Next. Okay, now I hand over Lynn. Thank you.
Thank you, David. All right, so yeah, that's bring us just to a very quick wrap up here. So we also, I mean, there are multiple, as you have now seen, there are multiple different ongoing research topics, many different aspects to think about here. And there's also, of course, many directions and open challenges. So we wanted to talk about some here. So we see there are many challenges in energy markets, energy trading. I just wanted to acknowledge that the perspectives of energy consumers and producers in energy trading is something that we've not talked about here in this presentation, and also we don't cover in much detail in the paper. But questions and open challenges are questions such as how do you price uncertainty and risk? How can you deal with uncertainty due to, for example, inability or unwillingness to share data or control of devices? So this could be due to, for example, low bandwidth communication or privacy concerns. Of course, we also have questions of integration across sectors, such as some multi-energy systems. How does uncertainty propagate between one system and another? And in these very complex models, how do we capture that in ways that allow us to treat it properly and not jeopardize security of the overall system? And then we also have many emerging challenges associated with decarbonization. So we are kind of all aware that there's a lot of, I mean, there's high impact, low frequency events such as hurricanes or wildfire ignitions. Those are not low frequency in the sense that they keep occurring and they might be occurring more frequently, but each and every realization of them might be different. So they can still be very hard to model. So there's also definitely scope there for additional work. Also, just understanding and trying to project and see out into the future, what are actually the impacts on the grid going to be? What kind of common mode impacts are we going to see? For example, if we have a cold spell and the wind stops blowing and the load goes up for heating, how is that going to impact the grid? And of course, you see so there's been multiple, of course, examples of such kind of common mode impacts, also through often extreme weather. And then there's one topic that is maybe a little bit less. I mean, there's been a lot of work on sort of operational uncertainty scales. How do we deal with uncertainty in sort of day ahead and weekly operation? Maybe a little bit less so on the seasonal variability and uncertainty. So how do we deal with a situation where we have a lot of excess renewable in spring and scarcity in winter? Of course, that is a question of energy storage and being able to keep and use the energy when we need it. But there's also a scope there for optimization or under uncertainty and treating this variability as uncertain scenarios, because these are, again, things that won't happen all the time, but sometimes they might. And then an ever ongoing challenge in stochastic optimization is scalability of our methods. So the problems here just quickly become complex and intractable. It's very hard, can be very hard to solve. And so it's very important here, I think, to remember that modeling and solution typically go very much hand in hand. And it's also important to remember that as we are, creating those methods, not only do we want to capture uncertainty, but we also have to be able to actually communicate and make it clear what is the impact of considering uncertainty. So, for example, like the 99% of the reserve capacity requirement is maybe something that it seems like people actually understand and want to adopt. But what does that mean? And so, yeah, how do you actually communicate around uncertainty? So with that, I want to stop here. Sorry, we've already taken a lot of time here. We got started a little late, but we wanted to open it up also for questions or thoughts from the audience. So thank you very much for being here. And yeah, we're hoping we can have a little bit of a discussion here now. Thank you. So also, so are there any questions from anyone? Okay, so we also needed to talk into the microphone. That's, excuse me? Have a microphone for a question? Sorry.
Hello, Vedran Peric, Technical University of Munich. Thank you for the nice presentation. This was a really nice overview of all the methods. But my thoughts that I would like actually maybe to ask just for a comment. All these methods are very fancy, but they all rely on this assumption that was mentioned. Okay, how do we actually estimate all these uncertainties? Is there some more effort actually how to really estimate all these uncertainties? Usually you say just it's relies on the previous experience, but it's kind of a very general thing. So is there some more effort actually to really get these uncertainties correctly?
Okay, so maybe I will start on that a little bit. So I think, yeah, as you say, I mean, being able to actually assess the uncertainty is a really important aspect of this, and it's a hard one. And sometimes it's challenging to know, to get access to data, or like how do you actually model correlations between different uncertainty sources. So definitely, like actually getting to a good model of the uncertainty can be very challenging in and of itself. I think. So I don't know, at least from working on transmission grid operations, I mean, just it can be challenging because even the historical data might contain both an exogenous uncertainty from, for example, renewable generation, but then it can also contain sort of uncertain or like changes that happen because control actions were taken. So distinguishing those can be hard. But then again, there are other situations, like for example, the reserve requirements, where you have historical data for imbalances. And there it's maybe a little bit more straightforward because you actually have access to the data. So I think it will depend very much on the application. And so there's both, I think, fundamental questions and in like how do you actually get the data that you need. And then there's questions of how do we, as researchers, get access to that data. And of course, that can be also a completely different question. I don't know, does anyone want to join?
One thought based on what your question was and what Lina was saying is that typically for short-term problems, data is quite available. For long-term problems, you have this problem that David showed in his graph, which I thought was very interesting. The future is extremely unexpected and tends to fire totally unpredictable scenarios to us. So for long-term planning, I think it's more difficult. For short-term planning, what's interesting is sometimes the data that you already have is sufficient. For instance, in static dimensioning, we were perfectly fine with 1 year of historical data. But then when we started looking at the same problem in a dynamic setting where you want to observe day-ahead conditions and adapt the sizing to those day-ahead conditions, you start cutting up that 1 year data into such small partitions that it's no longer sufficient. So then you have to develop statistical models that replicate the data if you want to apply machine learning algorithms that kind of try and associate day-ahead conditions to what to expect in terms of imbalances in the next day. So the generic answer here, it really depends on what you want to do. Whether you end up ideally you can just rely on historical data, but sometimes you have to go above and beyond and develop models that try and recreate the behavior of that data, even in short-term applications.
I like your answers. Nothing to add.
Okay. Any other questions, thoughts? Yeah.
Thank you for organizing this panel. It's really interesting. Thank you for the presentation. My name is Rodrigo Moreno from the University of Chile. And I want to ask a more practical question. I mean, what is your feeling about these models being accepted in practice for real decision making? I believe, for example, stochastic models, which add a lot of complexity into the process, can inform properly. For example, Tony was showing how his research is informing some processes to determine amount of reserve that can be shared. But I'm not sure if these models are actually being taken, or it's more about informing these amounts, and then these amounts will be plugged into the typical deterministic approach at the end for operation of power systems. So what is really your feeling regarding the gap between industry and academia?
I like that question, but I don't want to hold the conversation. Thanks, Rodrigo. So I really like the question, and it's always on my mind at least. And I think, for instance, I'm a huge fan of PSR, and one of the reasons I love PSR is because they've taken stochastic programming to the real world. What I showed here is something that was surprisingly fast research development to application. My impression from discussions with Svenska Kraftnät is they would like to use the method. Now you have to get on board all the Nordic TSOs because they have alternative methods based on imbalance netting to do these things heuristically. So you have to be part of that discussion and always try and communicate to every stakeholder involved what the method is doing, why the problem is challenging, why it's feasible given the available data. So it's always a matter of being part of that discussion. You can't just develop the software, hand it over and say, okay, good luck using it. It's an effort that goes over time. But what I did find surprising with this specific application was that from concept to application, at least within Sweden, it went quite fast. So I agree with your concern that in general it's hard to get some of these methods into control rooms or into applications, but sometimes the problem definition is by nature expressible as a stochastic program or a chance constraint program, and there you actually have a not bad chance of success in bringing that concept into practice.
Just a short thing. I think it highly depends on what applications you like to have. If you like to sell this application to one agent, for example, for bidding a strategy or whatever, at least my experience working recently with, I don't know, IBM or Siemens Gamesa, they are very open, at least in Europe. But when, okay, you talk with TSOs, right now how they derive their minimum reserve requirement, maybe it's very heuristic, maybe they are open. But when you bring this uncertainty modeling methods for more complicated things like market clearing, then all transparency and stuff, it comes, then I think it's a bit difficult to sell it. So we have to work on that.
And I just want to make one quick plug for PSSC 2020. So we actually addressed this question in a much broader context than stochastic optimization, but we looked at this, we had a panel discussion at the end of the last iteration of the conference looking at how does technology get, or ideas get translated from academia and research into practice. And so if you're interested in this question more broadly, on YouTube we have the videos from an hour-and-a-half long discussion on related questions.
Cool. Well, I will also add something, and that is that first, I mean, so one of the reasons we included security constraint optimal power flow here is because it is an optimization problem under uncertainty, which is of immense importance, right? So I think for me, it seems like the question of when do you actually adopt this? It's when you need it, you know, when it becomes economically important, when it becomes important societally, from a resilience perspective, I think that is when you really get that get this adoption. And I will just say that, I mean, working on some of the chance-constrained optimization formulations and also very closely with many different TSOs in Europe, and talking to them through this in the between 2012 and 2016, you start out and they think it's very exotic and scary, and then over time you see that okay, the amount of wind power uncertainty that is now on the system, they suddenly get more interested because there's the question of how do you quantify. So how do you quantify the impact of that uncertainty? So I think finding the ways in which you can communicate the outcomes of a stochastic optimization problem or problems under uncertainty is very important. Like how do you communicate, for example, renewable energy generation? What typically happens if you include uncertainty in an optimal power flow problem is that you end up with less transmission capacity than you would have had in a deterministic problem. Now, that is very closely linked to the concept of a security margin. And a security margin is, again, something that is a very kind of a normal concept and something people just used to think about. So I think the way you sell and talk about these methods also to people can be quite important. So yeah, that would be the way I think about it. But I think, I mean, there's a lot of questions around how do we, yeah, it needs to bring enough value to be adopted, right? Anjan?
Along those same lines, I'd like to point out that not all the decisions, I mean, there's characterizing the uncertainty is one issue, formulating the problem is another issue, depending on the application and so on. But some of the decisions will have to be by agreement, like standards, reliability standards, like NSOE grid codes and NERC grid codes and so on. Because, for example, I was just listening to somebody from the ISO in your part of the US, and she was saying that the big problem for her, if in determining the ancillary service market, the reserve market, is turning out not how to solve it, but how to determine what the reserve should be. Because, you know, the old method was the loss of the largest generator. Now, there is no agreement, there is no NERC standard, there is no NSOE standards. So I think that's a huge challenge for the industry to agree on these things so that, you know, those of us who are interested in the mathematics of this thing can actually solve with the real problems. Thank you.
Yeah, thank you. Anyone want to comment? Or?
I think in our case, one of the reasons the problem was deemed important was because it's an EU-wide legislation. So all of a sudden, all TSOs were affected. And also, back to Rodrigo's comment, I think there was an R&D culture within Svenska that also allowed this to, you have to be working with a group of people that are favorable to trying new stuff out.
I think there were questions there. There's questions there for.
Yeah, oh, thank you after, sorry.
Hi, my name is Paul from University of California, San Diego. My question is, in distribution grids, with a high penetration of DER, solar panels, inverters, demand response, what would be the challenges or what would be the approach when it comes to use uncertainty or when it comes to deal with uncertainty in these kind of power systems?
So the question of this uncertainty in distribution grids, right?
Grids,
Yeah.
yes.
So the way I think about that is that in distribution grids, I mean, there's a lack of observability. There's a lot of uncertainty sometimes about, how people are using their devices or are willing to control them. And I think that is a key application for optimization also under uncertainty potentially. It's like, how can you now, you can create frameworks where you're looking kind of at an adversarial model, for example, where you can think about what is the worst case reaction someone could have and how can you mitigate the impacts of those. That can be very conservative. So again, then you have to think about, how do you manage how do you manage to not be too conservative? But at least to me, I mean, it seems like there's a lot of uncertainty in distribution grids, and I think there are many problems there that can be framed as optimization problems under uncertainty. And of course, there's challenges also in distribution grids about different kind of, a little bit different physics, like three-phase systems and so on, that is different from transmission grids. And I think that's a very active area of research and something that I think many people here probably are working on as well. So I don't know if you had any more comments about it.
No,
yeah.
thank you. Thank you so much.
Yeah. Okay, so I think we will take one last question over here, and then we will let you. We are getting to the time about an hour from when we started, so we will let everyone go into the break.
Hi, I'm Mathieu from Georgia Tech. So first, thank you for the beautiful presentation, for the opportunity to have this discussion all together. For context, I'm a computational person. My job is to take the intractable problem, make it intractable. So here comes the question. Can we, as a community, so academia, industry, all together, come up with sort of targets, test cases, where we say, these are the problems, this is how fast they need to be able to solve. And if we can achieve that, then there's a chance that this can be applied in practice. Open question, I don't expect a yes/no answer, but if it can kickstart the discussion, that would be awesome. Thanks.
Anyone wants to answer? Otherwise, maybe David, should we pass it to you so you have the chance to also say something?
Yeah. So I would say what the thing that you are looking is how to hack some particular problem. I would say the power system community lags behind of computer science community in providing large scale a number of test cases, but we have seen during the last 5 years quite a lot of improvements in this sense. There are now libraries, they are open. There are even competitions similar to Kaggle competition that you may find, Dan was mentioning one is ARPA-E, in some particular our specific problems. I'm not really aware about how is working this competition, but I think they have already some targets, like how much time do you have to solve a security constrained unit commitment problem. So there are already some specific, and probably they are the most common problems one of the most common problems in power system. We don't have the full range of power optimization problem that we may find, but there are a few libraries and a few targets already in place.
Yeah, so to add on to that, David, I think that had been in discussion for a while with the ARPA-E grid optimization competition program to have some sort of uncertainty modeling in one of the challenges going forward. I think part of the reason they haven't done that, reading between the lines, is that it's exactly your point, is that we don't have an agreed upon formulation of this is the problem to solve. But if you want to try to influence that, then you should talk with Dick O'Neill and Corey Hedman and try to get that in Challenge 4 or something like that. But I think that is a really nice way to motivate the community to work on a particular problem.
And maybe also maybe that would also help with some of what you were discussing, Anjan, about actually, yeah, the agreement upon what is the goal is important, right? Any final, yeah? So, okay, I think then we've kept you 10 minutes longer, so we will not keep you anymore. I think there's a coffee break outside as normal. Thank you very much for coming, and we really appreciate it.